Okay, welcome back to Aero 206 Lesson 2 video. We're going to continue our work on Project 1, calculating the Breguet range equation for a jet aircraft. And we're going to focus today on using a function, creating our own function. We saw some functions last time, working with arrays and making sure we have good outputs for our program in terms of the figures that we're creating. Okay. Part 2 of the assignment right here is we're going to create a function inside our script that takes the inputs to the range equation and returns the range value that we found in lesson 1. Okay, so I don't have the full range equation here again yet. Hopefully you've got that now. This is just for demonstration, etc., etc. But the way that I'm going to create a function in my code, and this is an inline function because I'm creating it in the same M file that I'm using for my initialization and output, is I'm going to put this at the bottom of the M file, because I'll have everything else up here, and then this is just kind of down at the bottom. MATLAB will call the function whenever I ask it to. Okay, and the syntax to create a function is going to start off with using the word function to let MATLAB know that we're declaring a function. We're going to put the output of the function in square brackets. Okay, and we're going to say equals. We have to create a name for our function, so I'm going to say calculate range. And then we'll use parentheses, and this is where we list the inputs to the function. So in this case, I have 2 inputs to the function, row in slugs per cubic foot, and planform area in square feet. Okay, and then at the end of the function, I need to use the end statement here to let MATLAB know this is the end of the function. And I can see I can fold up this function, because once I get this function working, I don't really need to see it a lot. It'll just be at the bottom of my M file. But right now, I'll open up the function. Okay. And now up here in my main code, I'll call this function to get my output. And a good way to start off is just by copying my function here and pasting it up here. In this case, all the variables match up, so it's pretty easy, and I can do that. And now I can suppress the output, and now I can run this code, and it's going to call this function. It's going to send it these 2 things, and it's going to get this thing back out. So I'll press Control Enter here, and I get the same output. Okay. Now it's important to note that what's going on inside the function. The function is like its own ecosystem. Okay, the variables inside the function are local variables that can't be seen outside the function. So let's say that I wanted to make this a generic function for different units, and I just had row and S. I can change them there. Now, if I press Shift Enter, it will rename S inside the function, and I should have done that with row as well. Okay, and a lot of times for a function, just Y is good enough for an output. Okay, so now everything inside the function has different variable names, and if I come back up here to my main part of my code and press Control Enter, I still get the same answer, and it didn't look like anything changed because no numbers changed. But if I change a number here, I can see that my range changes there. Okay, so when it calls the function, it sends in this value in this variable. But inside the function, it goes in as this variable. It gets used for the calculation, and it comes back out as the variable y. And we can see this if we turn on the debugging mode and we run it. Okay, and we're going to step through it. So we see that it declared the row, the density variable. Okay, and now it declared the planform area. And now it's going to do the function call. And I'm going to step into the function. And now we can see inside the function, the only variables that exist in the workspace of the function, if you will, are these 2 totally different variables called row and S, different names. And it's going to create a value called Y here. And then when I continue stepping, it's going to output the fprintf statement. And then back at the, if I step out of the function, back at the top level now I have my variable r in nautical miles. And of course, it's not actually in nautical miles, but so that's how a function works. And one important part of a function is I would want to have good comments, again, inside the function describing exactly what's happening. And in this case, this comment pretty much does it, but I want to have comments everywhere inside the function, just making it really clear what everything is doing inside the function. Okay, so that's how to use a function in a MATLAB script. So that's step one there. Okay, and now we want to replace the single weight. So before there was the final weight of the aircraft here, weight 2 after it burns its fuel is 26,900 pounds. Okay, but now we want to ask ourselves, if we only burned 5,000 pounds, so we had a different final weight, what would be the corresponding range? And can we do that with a whole set of values of at least 20 values? And the way they're going to do that is by using the Linspace command. Okay, and the Linspace command creates a linear space of numbers between an input, between a start point and a stop point. And of course, I can just type in help Linspace if I'm not sure. So it's a linearly spaced vector between 2 points. And if I don't put in a third argument, this is important, so I'm going to maximize this. If I just put in an x1 and x2 into the vector, it's going to generate 100 equally spaced points. But if I put in a third argument called n, then it'll generate n points between the start and the stop. So if I do Linspace 0, 10, I'm going to get 100 outputs, and I can see my answer here is an array of 1 times 100. But if I do a Linspace 0 to 10 of 2, then I only have 2 elements, which is just the start and the stop. But if I do 10, then I have 10 elements. Okay, so that's how Linspace works. In the case of this project, we want to use Linspace between the starting weight and the ending weight. So, my first parameter would be 33,300. My second one would be 26,900. And I'd have at least 20 elements. So if I do Linspace 33,300 to 26,900 and put 20 spaces in there, then I get 20 values like that. Okay, and I can double click on answer to take a deeper look at them. Okay, but again, you wouldn't want to come into your code and type Linspace 33,300 26,900 with 20 values. Okay, because that's what's called hard coding numbers in your code. And instead of doing that, you'd want to set up a variable in your code where you call weight 1 33,300, weight 2 26,900, and then you can come up here and you say number of weights, so NW or N weights if that's more descriptive equals 20. And then you'd come down here in your Linspace command and say W1, W2, and N weights. Okay, that would be the better way to do it. If I comment out this function call real quick, I can place a % at the beginning, or I can just press Control R and it will comment out. Control T uncomments it, so that's a really easy way to comment stuff in and out of your code. So I'm going to comment that out right now because I don't want that to run, because I want to inspect the result of my Linspace command. Okay, so I press Control Enter on that, and now I'm getting this answer in my workspace, but it's just using the answer variable, and that's no good. So what I want to do is I want to create a new variable here and set it to the result of this Linspace command. So I'm going to call it W's because it's a vector of all the weights. So now I press Control Enter, and I'm going to suppress the output, and now I have this array of W's here. These are all the weights from the initial to the final, with 20 spaces in between. And now I've got everything programmed up nice and programmatically. I've got my input section in here where I set all my inputs, and that's important because I wouldn't want to have to come down looking in my code to change a hard-coded number down here. Instead, everything that the user could possibly input to the function, to the code, is up top at the top of the code. Okay, so now I've got this vector of W's in my workspace, and I want to inspect it, so I can just type in W's. Here's my columns. It's really poorly formatted because it naturally puts it in a row vector. I can transpose it by putting an apostrophe after it, and then I get a nice column vector of all my W's, so it's much easier to look at. The format's still not great. Sometimes you can change the format in MATLAB using the format command. Sometimes the bank format is actually really useful because it just puts everything in terms of like $sign with 2 decimal points. So sometimes using the bank format is really helpful. You can go back to using the short format if you want by typing in format short. Yeah, but you have to pay attention to the scaling factor at the top. Or if you really want to, you can do format long and look at all the decimal places in the world. Okay. Right now I'll just leave it on format bank. It's pretty useful most of the time. You can, again, if you want to see more formats, just go search the documentation for the other formats. Okay. Okay, so now let's say I want to do something with these W's, or I want to find out specifically what W19 was. I can type in 19. Okay, and because I only have a one-dimensional array, it really didn't matter that I put in both dimensions when I'm calling out this number. However, if I wanted to be most precise and correct, which is always best to avoid errors in your coding, I would want to keep in mind that this is a row vector, so it's the value I'm actually looking for is on row 1 in space 19. Okay, and that returns the correct number. If I had done 19 comma 1, that wouldn't work because there is no row 19 in this array. And again, I can double click on this array and see it's just all one row vector. Okay. Now if I did W's prime or transpose, then I could call 19.1, except it's not going to like that because I can't combine those two things. So if I just did X equals WS transpose, then I could do X 19 comma 1 because that's a column vector now. Okay. But now I messed up my workspace by putting in this X variable, so I just want to get rid of it. So I'm just going to type in clear X and I just get rid of that 1X. So now I'm back with my W's. Another really handy thing is, what if I don't know the exact number, but I just want to know what the last thing in the W's array is? I can just use the end command and it will tell me the last one in the array. What if I want to know the second to the last one? I can type in n-1 and it will give me to the second to last one. What if I want to add one thing onto the array, but I don't want to take the time to figure out the size of the array and actually type in 1 comma 21 equals 25,000? Shortcut is to do W's and plus 1 equals 25,000. Okay, and now I ended up with a 1 by 21 because I added another number at the end. Okay, so there's a lot of really cool stuff in MATLAB like that, but you want to use it judicially. You can get yourself in trouble if you don't understand what's happening exactly, but it is pretty powerful to be able to dynamically allocate arrays like that on the fly. Okay, so that's a little bit about Linspace. Obviously, there's other types of spaces like log space where we can space numbers logarithmically. Say that I'm going to calculate I want to calculate a range of ranges with a range of values like W's. And I don't have the full equation in here, so I can't use W's, so I'm just going to use a range of S's for now. So so I could overwrite S with just a range of values, okay? But you never want to just start overwriting variables with other variables. So, you know what, I'll leave it as W's. So we have a range of W's, and then I'm going to uncomment my function call line, and instead of sending in S, I'm going to send in a range of W's. So obviously it's all, you know, completely fake and not real at all. But now, but I'm just demonstrating how to send in a range of values to a function. Okay, so now if I execute this, it's going to run into a problem because, you know, now I'm sending in a whole array of numbers, but I'm trying to do one equation with a whole array of numbers. To do that, we're just going to tell MATLAB to ignore the dimensions, just operate on this array element by element. And so to do that, I'll come down to my function, and instead of using the times operation, I'll do dot times and dot divide. And this is vectorizing my code, so it works on the vector element by element. And now I can press Control Enter here. And my fprintf statement worked 20 times for each one because it was an array of values. But now in my answer here, I've got R in nautical miles, which is not really R, but I've got 20 values for it. Okay, so if your equation's working, you can do all that, and you should get 20 great ranges. Okay, just a couple other notes before we move on. First of all, it printed out 20 ranges because the size of this variable here that I'm sending to my fprintf function is an array of size 20. And that's kind of annoying, and really the only thing I want to see in the project turn in is that your fprintf statement is working correctly, so you only need to send in one value from this array into the fprintf statement. So I can send in the first value by typing in y equals 1. I can send in the 20th value by typing y equals 20, but that's not really coded up to be flexible because if I didn't have 20 values in my array, it would throw an error because it wouldn't be able to find value 20. If I always just want to send in the last value in the array, I can just use the keyword end here, and it will always take the last value in the array no matter what the array size is. So that's kind of a handy trick to use sometimes. So now in this case, if I run my code now, it only shows fprintf runts, which for the purpose of the project just demonstrates that your fprintf statement is working correctly, right? Obviously, this is not the correct range equation. Again, you need to go program in the range equation. The range equation needs a lot of other constants like CT, and CL and CD. Okay, do not program up those values here in the function. Okay, whatever they are. If you put them here in the function, this is bad for a number of reasons. One, every time you run the function, it's going to be reinitializing these variables, which wastes processing time because you're just repeating something over and over again. Two, is you wouldn't want to hard code in aircraft parameters like this into the function because the whole point of a function is to repeat the range command for possibly different aircraft in the future, and by putting this in the function, you're restricting yourself to only this aircraft with this CL, CD, and CT. Okay, so the right way to program up the rest of the range equation is to initialize all your constants up here, and I'm going to press Control I to get these things back over to the right indentation. Program up all your constants out here with the right comments beside them, and then pass those things into your range function as additional variables. Okay, and whatever other variables you need to look at the equation and figure out what you need to pass in order to make that range equation work that's in here, right? So you'd have to put them here in your function call, and you'd have to put them in the receiving end of the function where they go into the function. And now these variables will be available to use in the range equation, which is the correct way to put these additional parameters into the function. You would not want to hard code them into the function. Now, what we need to do is to plot the results in a figure and produce a good quality output figure. Okay? And so I'm going to create a new cell here, and I'm going to say create plots. This is my cell for creating the plots. Okay? And in my sample code that I'm giving you, I'm not expecting you to reinvent the wheel. I'm giving you a really good setup for a typical plot. Okay? And so I'm going to copy and paste this sample code out here into my script, and then we'll walk through it. Okay, so the first line of this plot command is I'm creating figure 1, and I do have 2 commands on the same line here, but they're okay, they go together. So I'm creating figure 1, I'm assigning that to a variable called f1, and then I'm clearing that figure using the clf command. Okay, so this is how I like to clear my figures on demand as I go. Sometimes it is still useful to close them all at the start of the script. Okay. The hold on command lets you plot multiple things on the same line. In this case, I've only got one thing to plot, so I'm going to get rid of this just for simplicity. We can talk more about that later. And I'm just going to retain one plot command. So here's the key command. This is plot, and this is x and y. Okay, so I'm going to plot x and y. And in this case, I'll plot my w's on the x and r in nautical miles on the y, and I'll give it a name. Okay, so let's talk about this plot command a little bit more. After the x and y inputs, then I've got my line spec for the plot command, and there's a ton of variables but to control with the line spec, but this is what's going to control the color, the thickness, the markers, etc., etc. So here's the plot command in the documentation. Highly recommend that you read through this. Here's the line spec variable that I'm passing in. And this controls the type of line, the type of marker, the color of it, etc. Okay, so right now in this line spec, I'm asking for a blue line that's dashed. And then I'm going to label this line's display name with the string called fake range. And this is going to be useful for my legend when I turn on my legend. So that's the plot command. I'm going to turn the grid on. You always want to have the grid on in your plots 99% of the time. I'm going to turn the legend on by telling it to appear in the northeast location of the plot. I'm going to set the X label to W's, which was pounds, and then I'll set the Y label command to range. Okay, and I'm just going to, and then I'm changing the font size on the entire figure. I'm going to comment out this line right now, and then we'll just take a look at it. So I just press Control-Enter to run it, and this is the figure that pops up. Okay. So if I didn't change the font size with this font size command, this would be the result that I would get. By the time that I put this into a Word document and turn it in, these fonts are going to be really, really small, and they're going to be almost unreadable. So I am giving you guys the right command to change the font size here, so this will never be a problem in anything that you turn in any future class. And the way this command works is you're going to set the get current axis, which is this figure right here, and you're just going to change the font size to 12. Okay, and you can see that my labels are showing up. My string for the X label is appearing right here. My string for the Y label appears in the Y axis. I can also set a title for this by using the title command. Again, titles are appropriate for standalone figures. If you're including a figure in a Word document or a report where there's a caption underneath it that says figure 1, then that's essentially the title of the figure, and you wouldn't want to put a title on the plot. So, okay, so if I press Control-Enter again, then I'm running this cell again, and I'm just changing the figure as I go, and I can see the title appear there, and that's really nice. So this is a great figure. Again, I can change my line spec. I can set this line to red by putting an R here. That creates a red line. I can put diamonds on the line by saying RD, and now I have diamonds at every data point. Okay, or I can remove this entirely, and then the default line is just going to be a blue line, and that's not going to help you a whole lot when you start having multiple plots. Okay? The way that we add multiple plots is with new plot commands. And now that I have multiple plots, I'm going to have to put back in my hold on and my hold off to hold these things on the same figure. Okay. Now this second one is going to appear to be the same line. So if I did it like this, blue dash dash up there. Okay, so obviously I can see the red diamonds. But I can also see the blue line. They're both the same data, but I can also change the data dynamically in the plot command. So I can say R divided by 2 and plot that, and then I get a second line that's divided by 2. Okay. So there's an example of having 2 lines. Now this second plot command, I can change the legend entry here so that it has a unique name. But now I can see that my legend is covering up part of my first plot line, and that's a classic mistake that you would never want to make. So I need to find a new location for the legend. And instead of doing the northeast, I could try the northwest corner of the plot. That's still covering it up. So I could just try the west location of the plot. And that's perfect because now my legend is not covering up any data at all. Okay. So that's a little bit about plotting. That's how to tweak your plot a little bit. I encourage you to use the documentation or Google liberally to figure out what you want to do with your plot. Finally, the last thing is to save it as a file that you can include in a report. So I'm going to say lesson 2 demo. So I'm going to save as the current figure, get current figure. The file name is going to be lesson 2 demo, and I'm going to save it as an EMF file. Okay, and we'll talk about these file types, and I'm actually going to save another one as we'll just do a JPEG or a PNG or whatever. Okay, so I'm going to run this now, and now when I come to my MATLAB main window here, I can look in my current folder, and I can see these 2 figure files that have appeared here. Okay, and lesson 1 demo is, and lesson 2 demo JPEG and lesson 2 demo EMF are both in the folder. So what's the difference between an EMF and a JPEG? Okay, I'm going to open up a blank Word document here. I'm going to go find those 2 files, and I'm going to insert them into my Word document. Okay. All right, here's my Word document. I'm not sure which file is which because I just dragged them both in here. Okay. So a JPEG is a rasterized image, which means it's created by a set of pixels. In this case, let's say the figure was 500 pixels by 500 pixels. That means there's going to be 500 squared pixels in there. And if I zoom in on the JPEG, what I'm going to see is that it's resizing those pixels to fill in new space, and that creates a lot of fuzziness and poor quality in the picture. Okay, so, and I have a feeling this is going to be my JPEG right here. Okay, if I zoom in on this JPEG, I can see a lot of fuzziness around the lines. A JPEG is not a precise way to store distinct changes in images. It's made for gradual changes in images and being very efficient at that, and that's why it's good for just pictures of regular things that you take with your camera. But for technical documentation, the more that you zoom in on this picture, And if you have to resize this picture in the Word document, so let's say that I had to crop something out, okay, and resize it. Well, now it's filling in, it has to resize the pixels, and it's filling it in with new information. It's just becoming even more blurry, okay. And so that's no good for a lot of reasons. Okay, it looks really poor. It's really poor quality. A lot of times the fonts will become really hard to read and stuff like that. Compare that with an EMF file. An EMF file is a vector graphics as opposed to rasterized graphics. So instead of having a set of pixels in this file, it has a set of mathematical instructions on how to draw these shapes. Basically a set of paths. Draw a line between here and here and color it this color, etc. Or put this text in here. And so what happens in an EMF file, when I zoom in on an EMF file, it redraws all of that information in the figure at the new scale that I want, and everything is crystal clear. So if I have to come in later and resize my figure for something, I can zoom in on the new figure and it's still all crystal clear. Okay. So, big surprise, the only type of file that is appropriate for documenting technical results and graphically is a vector graphics file. Okay. Sometimes you can get away with a rasterized graphic if you don't have to resize it or crop it or anything like that, but I will still be able to tell, and I am expecting vector graphics in my classes. Okay, an EMF is the native type of vector graphics file to include in a Word document. If you're working with LaTeX, it's an EPS file, encapsulated PostScript file. There are very, very, very few situations where using a rasterized graphic is acceptable in technical documentation. Okay. And we'll go back to our project 1, and I've already gone over how to add all of these labels and export it as a vector graphic. So that pretty much wraps up project 1. So this turn-in will be due by 07:30 on lesson 3, and I'll see you then.